Momentum is the motion of an object. It can be defined by the equation P equals mv. P will be momentum, m will be mass, and v will be velocity. When working with momentum, there is also something called impulse, which is essentially the change in momentum in a period of time, generally in the milliseconds. This leads us to the theorem J, which is impulse, equals F average times delta t, which is equal to change in momentum, which is demonstrated by the letter P. Impulse can also be measured as the area under a curve in a force by time graph. For curves graphs, this can be solved by taking the integral of the graph, which we use in calculus, which we won't cover here. For practicing impulse, we will use a ball being thrown at the wall having an average force of 500 newtons within 1 second of collision. What is the impulse of the ball? To solve this problem, we can simply use the impulse formula, giving us J, which is equal to 500 times 1, which is just going to be 500. In an isolated system, momentum will always be conserved. This is important to note because it means that the final momentum will always be equal to the initial momentum, giving us the ability to solve equations. In a perfect inelastic collision, the two objects that collide will stick together after collision with equal velocity, thus the name inelastic. Meanwhile, in perfect elastic collision, the two objects will move away from each other. Block 1 has a mass of 5 kilograms and is initially at rest. Block 2 is traveling towards Block 1 at an initial velocity of 10 meters a second and has a mass of 2.5 kilograms. Immediately after collision, the second block has a new velocity of negative 5 meters a second. What is the final velocity of the first block? Using the conservation of momentum that we discussed earlier, the final momentum will always be the same as the initial momentum. Therefore, we can use the equation m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. By plugging in the values, we get 5 times 0 plus 2.5 times 10 is equal to 5 times v1f plus 2.5 times negative 5. Further solving, we get 7.5 meters per second as the final velocity of the first block. Block A with mass 2 kilograms is traveling at 3 meters a second towards Block B with mass 5 kilograms at rest. They collide with perfect inelastic collision. What is the final velocity of the two blocks? Again, we will use conservation of momentum, but with the final momentum a little differently formatted this time. MAVAI plus MBVBI equals MA plus MB times VF. Now we can plug in the values to solve, giving us 2 times 3 plus 5 times 0 equals 2 plus 5 times VF. We then solve this, giving us our final velocity as 0.857 meters a second. The formula for momentum is still extremely similar to normal while being angular. Instead of P equals mv, now we have L, which is angular momentum, equals I, moment of inertia, times omega, which is angular frequency. If you're still unsure about the moment of inertia and angular frequency, make sure to check out our video on torque. Angular momentum is still done the same way and is also conserved. For our practice problem, we'll be using two identical disks, A and B. They will be colliding with disk A initially spinning at 5 radians a second, while disk B is at rest. Immediately after collision, disk B is spinning at 2 radians a second. What is the final angular velocity of disk A? Because the disks are the exact same size and the exact same, the moment of inertia, I, can be cancelled off of both sides, leaving us with omega AI plus omega BI is equal to omega AF plus omega BF. By plugging in, we will end up with 5 plus 0 equals omega AF plus 2. This leaves us with our final answer at omega AF, which is equal to 3 radians a second. As always, thanks for watching, and I hope this will help you.